Okay, so um, yeah, Gemini is here. I will set my time in this timer, and then okay, let's set this timer to 20 minutes first and solve the chemistry A. Okay, and then okay, then we'll take 5 minutes break. Okay, let's start with this. Let's start with this. Use this diagram to answer the following 7 questions. Okay, okay, these are here. I think this is a molecule. Okay, so my chemistry knowledge is not like a beginner. I know chemistry at some level, but not a, like a professional level. So let's see the first question. There are blah blah carbon atoms in the parent chain. Parent chain. It is called blah blah. Okay. I think parent chain is something like the main chain. Okay, let's see. This seems like a signal type of thing, type of molecule. Okay, so there are blah blah carbons in the parent chain. Oh, I forgot to set my timer. Let's set this first. Okay, let's go back to this. Okay, there are blah blah carbon atoms in the parent chain, and it is called something something. Let's say I like this one. Let's say this is the parent chain, and it has, yeah, I think every corner of this molecule has one carbon atom. So let's say this has three, but there's no three. Okay, let's count these two. Oh, okay, 1, 2, 3, 4, 5. Okay, let's say this has 5 carbon atoms, and actually I know the word for 5 is pentane, so I think I'm gonna go with this. Okay, let's move on to the second question. Numbering of this molecule will begin at carbon blah blah. Numbering of this molecule. Oh, I don't know what to do about it. Let's see. We said that this was the main chain, like the parent chain thing. So let's start from alpha. Let's start from here. Okay. Use this information along with the previous diagram to answer the following 5 questions. Okay. Okay. There are branches at carbons X, Y, and Z. Branch. Okay, these are called branches. Okay. The branches at carbon X are called something something. Okay. I think this has 2 carbons, and the should we? Oh, okay. Should we divide these two, or should we or shouldn't? Okay. Let me see if so that's common between carbon X and Z. So there should be a oh, these are common. then this means that we should divide both. So I'm gonna go with, okay, gonna go with this has two carbons. Let's see. And this is, I know this is type of a cyclic type of thing, but so I'm gonna go with, I think, methyl and cyclopropyl. Let's say, okay, let's say this. Oh, how much time do I have left? Okay. There's a type of branch that is common between carbon X and Z. So what is it called? So if I'm saying this is a cyclo type of molecule, then this is methyl. This should be methyl if I'm trying to be consistent with myself. Then I should go with methyl, right? Yeah, I should go with that. Okay. Which carbon is able to make another bond? Which carbon is able to make another bond? Okay. Branches. And one of the carbon is able to make another bond. Okay, let me see. Which carbon? X, Y, Z, and none of the above. Oh, okay. X, Y, and Z. So, I think carbon can make 4 bonds or something. So, 1, 2, 3, 4. I think this is set. 1, 2, 3, and the other. Okay, yeah. 2, 3, 4. So I think it should be Y. Okay. What is the IUPAC name of this molecule? Okay. I think I will only count the carbons, and yeah, I know this will be wrong answer because these branches names should be added in, but I'm gonna go with counting the carbons now. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, wait, what? Sorry, I lost my count. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay, let's say carbon 14. This this is horribly wrong, I think. Okay. Yeah. The addition of a methyl group onto carbon would cause change only to the name of the parent chain. A methyl group onto carbon something would cause a change only to the name of the parent chain. Okay, we know this is wrong now, but let me think. The addition of a methyl group onto addition of a methyl group. Methyl, I don't remember. I don't recall this, but I think it was CH3 or something like that. Yeah, I think methyl is this, and C2H6 should be ethyl. I think. I'm trying to recall my previous knowledge. So the addition of a methyl group onto carbon would cause a change only to the name of the parent chain. We said that this was the main or parent chain, and adding, but how can we add this? Oh, Oh, okay. Let's say uh, cause a change only to the name of the parent chain. Oh, okay. Let's say it should be close to the parent chain in here, if that's the real parent chain, of course. But since I have been assuming that this was a parent chain, okay, I still have time. Let's choose alpha this time. Let's say this. Not sure, but oh, I have a lot of questions. Which of the following molecules is not an organic molecule? So organic molecules should have carbon, hydrogen, and I think sometimes oxygen, fluorine, or something. Okay. Tetrafluoromethane, tert butoxide, hydrogen cyanide, and benzene. I think this is an organic molecule. I think this is an organic molecule as well. Hydrogen cyanide and tert butoxide. I Since I know this less than the others, let's choose this. How many valence electrons are present in butane? Oh, okay. How many carbons were there in butane? Let me think. How many carbons were there? Um, Valence electrons. I know what this is, but butane. Okay. Mono D3 butane. I think this mono D purple should be 3, I think, in butane. And yeah, I think this has 4 carbons in it. So butane, butyl. Okay. I should have known what type of molecule, organic molecule is this, but um, let me think. How much time do I have left? Okay, 9 minutes. CH, no, C4H, what? What should C4H? Okay, let me write this in here. C4H. Oh, sorry. I I'm not trying to search through Google. I'm just trying to see how many hydrogens can we combine with 4 carbons. Okay, let me think about this. So carbons shouldn't, and 416 plus, let's, let's say 26. I'm not sure. I'm just trying to be more logical. Which element has the same number of electrons as butane has valence electrons? Which element has the same number of electrons as butane has okay, I said 26, but I don't know which. I need to see periodic table for that. But let me guess. 2, 8, 10, 8, 18, and 8 left. So, no iron, zinc, chromium. Let's go with nickel. I don't know, actually. Which of the following functional groups? How much do I have? Okay. Which of the following functional groups is most likely to emit a pleasant sweet smell? Pleasant sweet smell. Oh, I know this should be a cyclic group. So RH, ROH, RCOH. This should be an organic molecule. So I'm not sure about that, but I think R was meant to be a radical, if I'm remembering this correctly, but yeah. Okay. RX. What is X? What was X? I forgot about this. Okay. COOR. I'm gonna go with this actually. Can your answer to the previous question participate in hydrogen bonding? Why or why not? Question. Answer to the previous question participate in hydrogen bonding. So, hydrogen bonding. Hydrogen has actually a bond called hydrogen bonding between fluoride, oxygen, and nitrogen, I guess. So, um, if okay, let's say yes, if the there is a F fluorine, oxygen, or nitrogen in the R group, then there can be a hydrogen bonding. Let me check this. There's group, then there can be a hydrogen bonding, or there can be not. It's just a general information, but I'm not thinking about its cyclic uh, characteristics, but whatever. I'm gonna go with yes. And with this explanation, which molecule, okay, how much time do I have left? Okay, which molecule will have the highest boiling point? Boiling point. Let me see. It should be hard to break it. So, they all seem like covalent bonding, and this seems like an ionic bonding, so I'm gonna go with this. How many hydrogen atoms does an alkane with n carbon atoms have? Oh, okay. Um, I don't know actually. How many hydrogen atoms does an alkane with n carbon atoms have? Okay, I think I'm gonna go. Oh, how much do I? Okay, I think how many hydrogen atoms does it have? I think I'm gonna go with let's say this. I don't remember this. Oh, okay. I need to be. Oh no, I need to be faster. To answer the following 5 questions, gives molecule name and boiling points. Okay. Have London dispersion forces. London dispersion forces. London dispersion forces. should be like a weak force or something, I think, if I'm remembering it correctly. Okay, I have 2 minutes left. Let's say, okay, let's say all of them. Let's say all of them. Assume each substance is a liquid at room temperature. Which of these molecules can mix with water? Can mix with water? Oh, I don't know actually. Ethanol, ethanoic acid, heptane, heptane and decane. Oh, I don't know. I'm gonna go with ethanol and heptane because this is lower than the boiling point of water. Ethanol and heptane, is that an answer? Okay, no answer like that. Let's say ethanol only. I don't know actually. Let's say I know it's incorrect, but because it has a lower boil, okay, link point than the water. Despite the decane does not have a permanent dipole, its boiling point is much higher than the ethanoic acid. Why? Does not have a permanent dipole, its boiling point is much higher. Decane can permanent dipole-dipole interactions and decreases boiling. Decane is unstable, straight chain contain the most carbon atoms. Two, one, two, three, four, two. Oh, okay, A. Let's say where. Oh, okay. Let's stop this and answer the last question. It's in the list. Methanol. Methanol is up to here, so all ethanol. Let's say. Oh, okay. Let me give 5 minutes. Let me give 5 minutes. Have a methyl group. Second answer the following questions. Methyl group 2. Which carbon would not produce a molecule with a side chain? Methyl group 2. Which carbon would not produce a molecule with a side chain? I think all of them would produce a side chain. The addition of a methyl group carbons would produce the addition of a methyl group which carbon produce the same molecule. Produce the same? It looks the same, I think. All additions produce the same molecule. Okay. Present in how many valence electrons are present in this molecule? Great question. Valence. Valence. Okay, so 4, 4, 8, 12, 16, 20, 1, 2, 3, 4, 5. Let's say 25. The maximum number of propyl that can be added to carbon of propyl groups. 2. I think it's 2. Let me say this. The electrons in a benzene molecule are not fixed on one atom. And the benzene are not fixed on one atom. No idea what this is. Let's say this. Oh, is it cyclic? I'm gonna go with the cyclic. An acid flavor compound has been discovered. It is naturally dissolved in organic solvent that is It is non-polar. It does not have any natural odor or color in the lab. We are presented with 5 vials that may contain the flavor compound. How will you attempt to detect its presence? Which orange dye will absorb it? Add water. An organic compound will readily dissolve in water. Create using HCl. Will decrease the pH past 0. But it says it's okay. It's an acidic thing. I think I would titrate with this with a base. 4. Okay, great. I have a lot of wrong answers. Okay, let me check this. How much time do I need to spend for this? Oh, I think I don't need any break. Okay. And okay, so for the first 30 minutes of your tutoring session, use the assigned model to the best. Increase your understanding. Oh, okay. Okay, then I need 30 minutes for that. Okay. We set the timer. Okay. Let's check every mistake that I did. There are characters. Okay. Let me copy this image and paste it in here. Let's ask this question directly. I'm wondering what it's gonna say. It is 6-hexane. Did I count the carbons in the parent chain? What did I say? I said this was the main or parent chain. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, then I am completely wrong. Identify the longest continuous carbon chain. The first step in IUPAC nomenclature is to find the parent chain, which is the longest possible continuous chain of carbon atoms. Longest possible? Oh, now I remember this. The chain from alpha to delta has 6 carbons. 1, 2, 3, 4, 5, 6. 3, 4, 5. Oh, okay. A chain from the end of the beta branch to the end of the. Oh, okay. The chain from the end of the beta branch and the here, okay, to the end of the delta branch also has 6 carbons. Okay. 2, 3, 4, 5, 6. That's okay. Other paths has 5. Okay. Apply the tiebreaker rule when there are 2 or more chains of the same maximum length. The parent chain is the one with the greatest number of substituents. If we choose the chain from alpha to delta as the parent chain, this here, okay. The substituents are at carbon Y, 1 complex group, at Y, 1 complex group, and let me see it from here. Y complex group, at X, 1 methyl group and 1 cyclopropyl group. Okay, 2 substituents. At Z, 2, this gives 5, and B to delta gives B, this here gives what? Y has a complex group, the entire alpha x branch. Okay, so in here, in here, I'm not sure about this actually. Kind of one complex, the entire alpha x branch. Oh, okay, this is gamma, this is y, okay. So here is 1, and then 1 and 1 in here, and then, okay, there are 3 substituents. So the parent chain should be like this. Oh, I got it actually. Substituents is selected as the parent chain. This chain has 6 carbons. What's the base name for a 6 carbon alkane? Is the base name for 6 carbon alkane is hexane. I actually understand this. Okay, let me move on to my number. Okay, I got it correctly, but now I understand why it begins at alpha. Now I get it. Okay, turns out I was correct about this, and I was correct about it too. Which carbon is able to make? Okay, this is nice. Oh my god. 2 cyclopropyl 3 ethyl. Okay. Let me ask this too. Okay, so the answer was 2 cyclopropyl 3 ethyl 2,4,4 3 methyl hexane. Oh, now I remember how the organic compound is named according to IUPAC. Okay. Okay, let's see it from here. 2 cyclopropyl 3 ethyl 2,4,4 3 methyl hexane. Okay. Let me open this image in here. Okay. Find the parent chain. Okay, we have found this. Number the parent chain. We number the chain to give the substituents to the lowest possible locants, position numbers. Okay, so numbering from A to delta gives 2, 2, 3, 4, 4, and the other direction gives 3, 3. Okay, so we choose this 3, 2, 2, 3, 4, 4, and then identify and name substituents. Okay, so 1, 2, 3, 4, 5, 6, 10. Okay, okay, got it. At position 2, cyclopropyl. This is a cyclic molecule, and it has 3 carbons, so which is cyclopropyl. Okay, this makes sense. And then methyl group. So methane is CH3 as far as I remember. So CH2 should be a methyl group. So okay. At position 2 we have cyclopropyl and methyl. At position 3 there's an ethyl group which has 2 carbons. Okay, that's okay. At position 4 2 methyl groups. At position 4 methyl and methyl. Okay, got it. Alphabetize and assemble the name. We list the substituents in alphabetical order in prefixes like D or 3 and combine them with the parent name. Combine the 3 methyl groups. 2, 2, 4, 4. Oh, okay. 3 methyl. Okay. The alphabetical order of the substituents CEM. So we start with cyclopropyl, then ethyl, then trimethyl, and this is a hexane. Okay, I got it. Got this. Okay. How much do I? Okay, I still have time. Let's move on with this. The addition of a methyl group onto carbon would cause a change only to the name of the parent chain. So the correct answer is okay. I don't know about this. Let's ask. The addition of a methyl group onto carbon delta would cause a change only to the name of the parent chain. Oh, so it should change the name hexane. So if we put in here, I got it. But okay, I need to check the Gemini's response to be able to make sure about this. The addition of a methyl group. Carbon 6 was delta, right? 1, 2, 3, 4, 5, 6. Yeah, this was. Analyze the group. We need to add the methyl group. Okay, parent hexane chain. Changing parent hexane to heptane. Okay, I got it. Well, we had the options. Test the outcomes. Methyl heptane. C6 is the only. Okay, that makes sense. I can actually understand it now. Okay, which of the following molecules? Okay, let's ask this, but give the information that it's another question. It's okay. I'll ask another question that is not related to the image I have sent before. Which of the please answer and explain. Which of the following molecules is it's not an organic molecule? Okay. Hydrogen. Oh, it has cyanide. I told this. I told that if an if a molecule is an organic molecule, it should contain carbon, hydrogen, and sometimes fluorine, oxygen, and nitrogen, or some other things that I'm not aware or I don't recall. But cyanide, I I told this. Okay. The definition of an organic molecule is centered on compounds containing carbon, particularly those with carbon-hydrogen bonds. However, there are a few historical exceptions: benzene and tetroxide. These are classic organic molecules. They are built on a carbon skeleton and are rich in carbon-hydrogen bonds. Tetrafluoromethane. This molecule is considered an organic compound. Although it lacks CH bonds, it's a derivative of methane, fundamental organic molecule. It belongs to a major class of, okay, got it, called organohalogens, okay. Hydrogen cyanide. This is the correct answer. While it contains both carbon and the SCH bond, hydrogen cyanide and other simple cyanide compounds like KCN are traditionally classified as inorganic. This combination places them in the same category as other simple carbon-containing inorganic compounds. Why is why are cyanide compounds considered inorganic? Please explain in detail. Okay. I'm curious actually. How much time do I have left? 15. Oh, I can see it from here. Okay. Primarily due to a combination of historical classification and their distinct chemical properties, which make them behave more like inorganic salts than typical organic molecules. Here's a detailed breakdown. Historical, okay. Chemistry was based on the vitalism theory in 1890. That organic compounds could only be produced by living on vital force. Inorganic compounds were those derived from non-living rocks. Cyanides were first isolated studied from mineral-like sources. For example, the famous pigment prism blue is ironite. Without a living oven, high temperature reactions, charcoal and atmospheric nitrogen, which placed them firmly in the inorganic camp. Okay. Even though the cyanide and simple compounds align more closely with inorganic chemistry. So halides, soda halogen. Oh, interesting. This compound chemical reasons the cyanide ion like a halide ion. Chloride, for example. Soda halogen. Okay, interesting. Always been potassium cyanide primarily. Oh, right. This is correct. Okay, I got it actually. Let's move on to my another. I was right about the valence electrons that were present in butane, but I didn't get it from here. Okay, let's ask this. Let's ask this, but I'll say that again so that it's not confusing for the model. Chromium, nickel, zinc. Okay. So the correct answer is iron. And yeah, it's correct. To solve this, we first need to find the number of valence electrons in the butane molecule and then find which element has that same number of total electrons. Butane, yeah, alkane with 4 carbon atoms, so C4H10, 4 and 1, and yeah, this is the way I was thinking. For a neutral atom, total electron number is equal to the atomic number. We are looking for the element with an atomic number of 26. So actually I was correct before, but I didn't have a periodic table in front of me, so I think it's okay. Let's ask this too. Okay, for now Let's try to ask this without saying that I'm asking a different question. Oh, okay. I had no idea about this question, apparently. The following function is most likely to emit a pleasant sweet smell. RCOOR prime, RCOOH. This general formula represents an ester. Esters are a class of organic compounds well known for their characteristically pleasant, fruity, and sweet smells. They are primary aromatic compounds responsible for the natural scents of many fruits and flowers. Okay. ROH is an alcohol. Have a sharp, distinct chemical smell. RCO. Oh, this was carboxylic acid. Okay. It should be sour, pungent, often unpleasant. Okay. Alkyl halide. Halide. Okay. Those have sharp synthetic smells and are commonly used as solvents. Okay, I got this. I got this actually. Oh, how much time do I have left? Okay, I have 10 minutes. I still have 10 minutes. Can your answer to the previous question participate in hydrogen bonding? Okay, it was a no question. I think it was because these groups, now that I remember, ester groups are cyclic groups, so maybe it's not an answer, but let me clarify this by asking it to Gemini. Oh, it says yes. Uh, but I have asked. Did I ask another question? I may have made a mistake there. No, I did not. Did I ask this question before? The following is most likely to emit a pleasant. Okay. Okay, there are different answers now. An ester can participate in hydrogen bonding, but only as a hydrogen bond acceptor. So it's a conditional yes. It's not a general yes. To participate in hydrogen bonding, a molecule needs one of two things: hydrogen bond donor, hydrogen atom directly bonded to a highly electronegative atom. Yes, this was my point actually. Lone pair of this was my point actually too. Ester functional group can be an acceptor. An ester has two electrons, both of which have lone pairs of electrons, so can attract hydrogen molecule. Oh, I can't donate hydrogen to molecules cannot hydrogen bond with each other. This is why. Okay, I think this is a debatable answer. Let's ask if this is check if this statement is accurate. How many questions do I have left? Okay, I need to be faster. Partially accurate but misleading. I I'm not an expert in chemistry, but accept Gemini's response on this. Okay, let's move on to another question. Did I miss something in here? No. Let's see. Which molecule will have the highest boiling point? Let's ask this. Highest boiling point. So CH4, these are like carboxylic acids as before. But I was thinking this seems like an ionic molecule, so HCOH, boiling molecule determined by string of forces, the attractive forces between molecules strong. IMFs require more energy to overcome. Formic acid, carboxylic acid. It can form hydrogen bonds, which are the strongest type of IMF. Acids can form stable pairs called diamides, making their IMFs exceptionally strong. Okay. Okay. The weakest type of IMF. Oh, not that. I was actually wondering about CH3Cl. This is a polymer due to chlorine atoms, so it's which are weaker than hydrogen bonds. Oh, okay. I got it. This is an ester molecule, so it says that, but it cannot hydrogen bond with itself. So you're agreeing with the answer in this here. Okay. Let's check the questions from here as well. Let's put in here as well. Okay. 13A COH. Okay. Same. I get it now. Okay. How much time do I have left? Okay, 4 minutes. I still have 4 minutes. How many hydrogen atoms does an alkane with anchor? Okay, I have to ask this. Correct answer is 2N. Let's check it from here as well. 14. 2N, yeah. Okay. What was that? Okay. How many hydrogen atoms does an alkane with N carbons atoms have? 2N. Okay. The general formula for an alkane is CnH2n, so this makes sense now. This formula is derived from the formula for an alkene. Okay, this is alkane, this is alkene. Oh, okay, we just separated hydrocarbon to create the carbon. Oh. Alkene with N carbon atoms have. So, number of hydrogen atoms. Oh, okay. This has a double bond. So Alkane has a single bond and alkane has a double bond. I get it. Okay, that makes sense to me. I assume each substance is a liquid at room temperature for these molecules. Okay, let's copy this image and then ask this question because I had no idea. I still have 2 minutes. Can they mix? Why can they mix with water? Oh, okay. Ethane and ethanoic acid. They both can participate in hydrogen bonding. Okay, it's all about hydrogen bonding at this point. So able to do so, like dissolves like, oh, right. Able to go around like dissolves like, it's the same thing. Is a polar molecule. Water is a polar molecule. Other polar molecules. So ethanol and ethanoic acid are polars, and heptane and decane are hydrocarbons, which means they are nonpolar hydrocarbons. Okay, I get it. I get it now. Let's ask this. Right, that decane does not have permanent deposed boiling point. Why? Okay, let's copy this before my 30 minutes ends. Let's ask this too. Present in this molecule. Valence electrons. 1, 2, 3, 4, 5. So 5 times 4. 20. And are these 20? And 1, 2, 3, 4, 5. Oh, right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, okay. This should be 30 now. I get this. Electrons in benzene are not fixed on one atom. They are delocalized. I have to ask this too. One last thing, and then I will be understand everything. Okay. Despite that the cane does not have a permanent dipole, its bond weight is much higher than ethanoic acid. Why? Contains the most carbon atoms. Seems counterintuitive. Explain cumulative effective of London dispersion forces. Okay, I don't have much time, so I will only ask this. And then move on with the next part. I'm trying to understand what is. Okay, so let's move on with the next part because my 30 minutes has ended. And what should I have done? Okay. I should ask these. Okay. Let's start with this. Okay, let's set the timer first. 15 minutes for this. What is this? 15. What are the IUPAC rules on naming straight chain alkanes? I think I understand this. Let's see the answer. Certain alkane are based on a simple two-part system, a prefix that indicates the number of carbon atoms followed by a suffix a. Okay. The core rule prefix plus suffix. This part of the name specifies the exact number of carbon atoms in continuous chain. For a chain of 5 carbons or more, the prefixes are derived from Greek numerical roots. The first 4 prefixes are historical and must be memorized. Suffix A. This ending signifies that the molecule is an alkane. Oh, okay, because I have asked this. Okay, meaning it's a saturated hydrocarbon with only carbon-carbon single bonds. Methane, ethane, propane, butane, pentane, hexane, okay, heptane, octane, nonane, decane, oh, decane, dodecane, dodec, okay. Straight chain algeometric arrows use prefix prop. A, propane, 8, octane, octane. Okay, I get it. I understand it. Let's move on with the second question. What are the most well-known physical characteristics of alkanes, esters, carboxylic acids, and aromatics? Okay, let's see. I'll try to finish all the questions in 15. If you do not finish them all, move on to the next section anyway. Okay. Solubility. Okay, others, boiling point, others, aromatics. Okay, let's see. Alkanes are non-polar. Following the like dissolves-like rule, they're insoluble in polar solvents like water. Think oil and water, but soluble in other non-polar solvents. Okay, alkanes are non-polar. They're not soluble in water. Boiling point, their only intermolecular forces are weak London dispersion forces. Boiling points are generally low, but increase predictably as the carbon chain gets longer. More surface area, stronger LFDs. LDFs were okay, got it. Small alkanes are odorless, while larger ones have characteristic smells like gasoline. At room temperature, the small alkanes are gases, mid-sized ones are liquids, and larger size are waxy solids. Okay. Odors, esters. This is their most famous characteristic. Esters are known for their pleasant, sweet, and fruity smells. Natural sense of boiling point esters are polar but cannot hydrogen bond with themselves. Their boiling points are higher than alkanes of a similar size but significantly lower than alcohols and carboxylic acids. Okay. I'm thinking this like a perfume. Small esters are somewhat soluble in water because their hydrogen atoms can act as hydrogen bond acceptors. Solubility decreases rapidly as the carbon chains get longer. Okay. Um, somewhat soluble. Okay. Oxalic acids, they have exceptionally high boiling points for their size. This is because they can form a stable dimer, where two molecules are held together by two hydrogen bonds at once, requiring a lot of energy to break apart. Okay. They're known for sharp, sour, unpleasant, pungent with vinegar, which is a solution of ethanoic acid. Completely mixable. Water due to their ability to form a strong hydrogen bond solubility. The nonpolar carbon chain gets longer. Okay. Aromatics. The name aromatic originally comes from their distinct strong smells. These can range from pleasant, sharp solvent like benzene itself. Their defining feature is flat, planar ring structure with delocalized pi electrons, which makes them very stable. Okay, these are the things like I was thinking as a cyclic. Okay. Most simple aromatics like benzene are nonpolar and therefore insoluble in water. Their flat structure allows them to stack efficiently, leading to effective London dispersion forces and higher boiling points than non-aromatic compounds of a similar size. Okay, got it. I think I have a problem with the boiling points. But let's ask the other question. What are non-metallic and non-ionic intermolecular bonds? What is normally their hierarchy, and in what case can LFDs overtake hydrogen bonds? Non-ionic intermolecular are bonds, non-metallic and non-ionic are hydrogen bonds, dipole-dipole interactions, and London dispersion forces. Non-metallic, non-ionic. Okay. Hydrogen, dipole-dipole, and London dispersion forces. In what cases can LFDs overtake? What is normally their hierarchy? What's meaning of hierarchy in here? And in what case can LDFs overtake H bonds? Hierarchy of strength. Okay. Thermonuclear force, often called van der Waals forces, are the attractions between neighboring molecules. For molecules of a similar size, their typical hierarchy from strongest to weakest is. Oh, hierarchy is the strength of the hierarchy. Hydrogen bonding is the strongest type, and specifically NOF, because hydrogen has bonded to hydrogen. Hydrogen acts like a partially positive thing, and yeah, I know that. Dipole-dipole interactions occur between polar molecules that have a permanent separation of positive and negative charge. Permanent dipole. Polar molecules. Okay, London dispersion, the weakest type of intermolecular force. They are caused by the random movements of electrons, which creates temporary instantaneous dipoles. LDFs exist in all molecules. LDFs can be stronger than hydrogen bonds when comparing a very large molecule to a small molecule. The strength of LDFs depends directly on the number of electrons and the surface area of a molecule, while a single hydrogen bond is much stronger than a single LDF interaction. A very large molecule with many electrons can have a powerful cumulative LDFs. Classic example, decane and water. Water is a small molecule, but its molecules are held together by strong hydrogen bonds. Its boiling point 100 degrees. Decane is large, non-polar hydrocarbon that only has LDFs. However, because it's so large and has so many electrons, the combined effect of LDFs is much stronger than the hydrogen bonds in water. As a result, its boiling point is 174 degrees. Case where the cumulative. Okay, I got it. Okay, yeah. Let's ask this now. I have 5 minutes left. In what case can the strength of LDFs vary between two molecules, even when their molecular formula is the same? Isomers. Okay, this happens between structural isomers, which means molecules that have the same molecular formula but different arrangements of atoms in space, I think. Strength depends heavily on the surface area of a molecule, even when two molecules have the same number of atoms, same number of electrons, and their shape can drastically change their LDFs. Strength change and branched chain. These molecules are long and cylindrical. Their large surface area allows for many points of contact with neighboring molecules, leading to a stronger cumulative LDFs that are more compact and sphere-like. Their smaller surface area reduces the point of contact between the molecules, resulting in weaker LDFs. Pentane. So, N-pentane and neopentane. Okay, long, large surface, boiling point 36 degrees. Okay, they have the same with the strength. and pentane has longer, stronger LDFs and has a significantly higher boiling point due to its larger surface area. Okay, I got it. Let's ask this question then. How do I count valence electrons in an alkane by looking at this carbon skeleton? I think I might know that, but let's see. Okay, count the number of carbon atoms and use the formula 6n plus 2. Okay, count numbers and 6n plus 2. Pentane, 5 carbons, um, 32 valence electrons then. Oh, forgot to write from the basic definition of electron and general formula for the alkanes. CnH2n plus 2. So 4n like this, and yes, 2n plus 2, this remains the same, and it gives, oh, it makes a lot of sense actually. Okay, got it. Let's ask the last question. How can titrations be used to identify molecules? Titrations can help identify unknown weak acids or bases by determining two key properties: the molecule's molar mass and its pK or pK. Okay, this is like a pH thing. Okay. If you start with a known mass of an unknown, so is it only work for weak acid? Is this works for strong acid or bases? Let's see, if you start with a known mass of an unknown solid acid, you can titrate with a strong base of known. Oh, okay. The moles. Okay, for 1-to-1 acid-base reaction, the moles of the unknown acid are equal to the moles of the base added. You can calculate the molar mass of the unknown molecule using the formula molar mass equals mass of unknown and over moles of unknown. This calculated molar mass can be used to narrow down and confirm the identity of the molecule. pK is the acid dissociation constant, unique value that acts like a fingerprint for every weak acid. As you perform the titration, you can measure the pH after each addition of the titrant, creating a titration curve. On this curve, you can find the House equivalence point, where exactly half of the unknownness has been neutralized. The pH of the solution at the half equivalence point is equal to the pK of the acid. Okay, I think I understand it. You can then compare this experimentally determined pK value to a list of known pK values to identify your unknown acid. Proton is a polyprotic. I think for polyprotic show multiple for each. The number of electrons per interact that tells you how many nasty proton. And a crucial piece of, okay, interesting. Is this still generating a response? Oh, interesting. But I have no time left, so I have to stop it. Okay, let's see. I have to download and attach these. Okay. Let's download it. And this. Oh, wait. Okay. And then I have to, oh, sorry. And then let's ask this. Give the model your answers and ask it to mark you. Yeah, okay. Let's set this timer after adding this. Let's set this timer. Okay, let's take these two. Okay. After that, what should I do? Take a break in 20 minutes. Okay. Let's set this timer to 10 minutes. Great. Using the diagram from chemistry PB. Oh, I should have opened these, right? Okay. Let's open these too. Okay. What are the names of the branches at carbon Z? This is B. Okay. What are the names of the branches at carbon Z? At carbon Z. This should be methyl, and this should be propyl, I think. Okay. Which of the following molecules has the lowest boiling point? Oh, wait, I think I should have only sent the chemistry B, right? Okay, so I'll ask this again. Okay, sorry about that. Okay, let's set this timer to 10 minutes again. Using the diagram from page 1, what is the name of the branch at carbon Z? Page 1. Okay, let's see. Is this the correct one? Yeah. branch at okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is our okay, this should be our paired chain. So this should be it. Methyl. Yeah, okay. 1 C. Which of the following is not an organic molecule? Methane, methanol, carbonate ion, chloroform. Oh, carbonate ion, chloroform. I think it's carbonate ion. I don't know, but yeah. How many valence electrons are present in ethane? Valence electrons. Oh, what was the 6N? But is it an alkane? Ethane. Alkane. Yeah, this is an alkane. 6N plus 2. Yeah. So 2 times 6, 12. Then it should be 14. Using the diagram from page 5. Page 5. Okay. What is the maximum number of ethyl groups that can be added to carbon beta? Maximum number of ethyl groups. So this has 2 carbon bonds and 2 hydrogens, so we can remove hydrogens. Let's say it's 2, but okay. Why every? Answer is C. Let's see. Write the answer in the space provided. What is the impact name of the molecule shown in the diagram on page 5? Oh, okay. Interesting. This is a chain. 1, 2, 3, 4, 5, 6. 6. Butane, hexane, heptane. Is this an heptane? Let's say it's an heptane. But do we have any branches? Okay. No, we don't have. What to do right now? I'm gonna go with heptane. Let's move on with 6. Using the table on page 4. Okay. Explain why decanoic acid, okay, has a much higher boiling point than methanoic acid, even though they are both carboxylic acids. Oh, okay. Methanoic acid and decanoic acid. So the last 2. Okay, so since there are more carbon on in decanoic acid, the chain is longer than methanoic acid, therefore more LDFs are present in decanoic acid, which results in higher boiling points. I think I have learned this. Oh, it did give an answer key, but I don't want to look at it I will just ask. These are my answers. Please mark it. Oh, I think I have. Oh, 5. Which one is incorrect? Heptane? Oh, hexane. I confused it. But what was the thing for 5? Okay, methane, ethane, uh, propane, butane. Okay, what was the thing for 5? Hexane. And then heptane. Heptane's 7. Oh, okay. I get this now. Okay, I really understand it now. I have asked this. I think I don't need any breaks. Let's select the other version that I. Okay. Now we're moving on to the post test right now. Do I need this? Okay, I will set this timer to 20 minutes and I will start solving post test. Do I need to? Yeah. And please go final surveys. Do I need to complete this during the video? I don't know. Okay. Use this diagram to answer the following 7 questions. But this was the same as before, isn't it? Okay, let's do the post test. Well, these are both chemistry A. Why? I need to solve chemistry B. Okay, let's open this in here. Yeah. Okay. Use the following diagram to answer the next 5 questions. How many carbons are in this molecule in total? Okay. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12, I think. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. How many carbons? How many carbons are in the longest chain? Let's see. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, 6, 7. Both are 7. 1, 2, 3, 4, 5, 6, 7. 6, 7. Yeah, 7. Okay. From which carbon will numbering begin? Oh. Alright. I think we should start from here because the branches should have the smaller number. So 1, 2, 3, 1, 2, 3, 4 in here. Let's see if we start from here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Let's say 1, 2, 1, 2, 3, 4, 5, 6, 7. 2 and 3. 2, 3, 4, 5, 6. 1, 2, and 3. What about this? 1, 2, 3. Oh, 3, 4, 5, 6. It gives 6. Oh, then delta, I think. Yeah. What is the name of this molecule? That's a great question. Okay. So, what was the name for 12? Decay is 10. Cane, decay, cane, decay. Cane, cane. Oh, yeah. Dodecane. Yeah. Okay. So, dodecane. Is this? Okay. Yeah, this is correct. So, yeah. Okay. Right. We're starting from here, and 2 has methyl. 3 has 2 methyls, right? Okay, then 2, 3, 3. 1, 2, 3, 4, 5, 6, 7. Okay, 2, 3, 3 methyl. Let's write this 2, 3, 3 methyl. And methyl 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4 has ethyl. So I need to write ethyl before methyl because it needs to be in the alphabetic order. So 2, 3, 4 ethyl. Then yeah. Okay, so let's erase this. 4 ethyl. Oh, is this correct writing? I don't know. How much time do I have left? Okay. The addition of an oh, it's written in here. Group to which carbon would change the numbering order. So we'll change the numbering order. It can be delta. Can it be delta? Why did I start in here? 1, 2, 3, 4, 5, 6. No. I should start here or from here or from here. So if I add this in here, nothing would be changed. If I add this, add what? Ethyl group. Oh, sorry, which? So let's say if we add this in here, ethyl group in here. 1, 3, 4, 5. 1, 3, 4, 5. 3, 4, 5, 30. Okay. So 1, 2, 3, 5. 2, okay, this doesn't change anything. What about this? Oh, it changes the name of the parent molecule if we add it in here. Numbering order. I think delta. Yeah. Let's see. Which of the following sets of molecules contains molecules made up of exactly 8 carbons? 8. Octane, octene, ethyl octane. So heptane octane. Octane should be the correct one. Heptane 7, hexane 6, nonane 9, so octane 8. Yeah, okay. How many hydrogen atoms are in an alkene? Alkene with N carbons. So alkane should have single carbon-carbon bond, and alkene has double, and I think this should have triple. So let's say if it has two carbons, then it would have two carbons and two hydrogens. If it would have three carbons, can it have three carbons? If it has, then one, two, three, four. There is no triple bonds. What am I saying? I'm sorry. I think I'm just two double bonds. Yeah, triple. It can be triple, and then carbon, carbon, carbon. Then I'm gonna go with N. Which of the following molecules is most likely to taste sour? Then it should be an acid. I think this should be a carboxylic acid. Okay. Use the following list of molecules and their attributes to answer the next four questions. Which molecules have permanent dipoles? I remember something like that. Permanent dipoles. Permanent dipoles. Dipole connection. Ah, okay. I don't remember that. It should have these two or these two, I think. Okay, let's say this. What is the most likely explanation for the large disparity? Disparity, oh, okay, between methyl cyclopentane and methanoic acid. Pentane and methanoic acid disparity. Um, one is acid. Methanoic acid has a permanent dipole. Acid can participate in hydrogen bonding. Yes, it can. Oh, then the answer should be like this. Okay. Method. Large disparity between this. 5-carbon ring is much more unstable than method. I'm gonna go with this. Okay, just wait. This question. I forgot about health. I have 7 minutes left. I'm gonna skip this. Where would you accept pentanol to place in this list? Pentanol. So 5-carbon alcohol. Alcohol should have lower boiling point, so it cannot be in here. But I think it will be between the ethyl ether and methylcyclopentane. Yeah, okay. Use the following diagram to answer the next 2 questions. How much time do I have left? Okay, 6 minutes. When this molecule is part of the main chain, it is called, this is a cyclic something, and propane should be a correct thing. Okay. When it's, oh, it's a main chain, it's a cyclopropane, it's a side chain, it's a cyclopropyl. Yeah, this is a correct thing, I think. This molecule can be categorized as which of the following? I Aliphatic carbohydrate. I'm gonna go with aromatic. I think, yeah. Which of the following is not an organic molecule? I know that. Use the following diagram to answer this next 6 questions. Assume that addition of an alkyl group to any carbon will not break double bonds. So it won't be added in here. It can be added in there. Yeah, okay. So now a methyl group to methyl alkyl. Is that the same thing? Yeah. Oh, I think I made a mistake before. Okay, no man. Group 2 addition of a methyl group to each carbon would not produce a molecule with a side chain. I think it's E epsilon. The addition of methyls to which carbons would produce the same molecule. Addition of methyls to which carbon would produce the same molecule. Produce the same molecule. Interesting one. Alpha and gamma would break. Oh. Produce the same molecule. How can it produce the same molecule if we add something to it? Oh, at the same time. Okay. Interesting. Yeah, I'm gonna go with alpha and delta. What is the maximum number of methyl groups that can be added to carbon beta? So it has 3 bonds now, so I think 1. What is the maximum number of propyl groups that can be added to carbon E? Of propyl groups can be added to carbon E. So 3, I guess. Yeah. Which intermolecular forces are present in this molecule? Let's see. Hydrogen bonding, I guess. Along with the previous diagram, use the following diagram to answer the next question. Which molecule would you expect to have a higher boiling point? Oh, interesting one. There's no oxygen in here. Why did I write hydrogen bonding? London dispersion forces. So 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons are present in here. Justify your answer. How much time do I have left? 2 minutes. I think the first diagram. Sorry, first molecule would have a higher boil boiling point because because LDFs are because the existing LDFs are can result to have more strength than the hydrogen bonding in the water molecule. Okay. I, oh no. Describe it. Oh, you're a chemist who needs to test what molecules are contained within a vial. You believe that it contains ethanoic acid. You have access to any element on the plate to perform describe titration, I think, because this is a weak acid. You use a device to determine the molecular structure of this molecule. It contains two carbons. That as a constant, it has two hydrogen atoms. What kind of molecule do they to be? Two carbons and two hydrogen atoms. I think this theory that this molecule is a carboxylic acid has been confirmed as an alternate method. Okay. You find that the molecular weight is 8. Does this result suggest? No idea. If your classmates there were two carbons, what would be the molecule? Like 812. I'm gonna go with this because I don't know. Okay, let's see. 3 methyl. Oh, okay. 3 out of 5. Oh, I think my point is higher now. Yeah. What was that? But I got this correctly. Titration was the answer, so I can say it's 12 correct answers. Then I use Gemini next. I think I would like to use this. Yeah, I would. But there was a moment that the answers were different in the Gemini response and the given answer PDF, so I would rate this 4. I found the model unnecessarily complex. No, actually, the model is easy. I thought the model was easy to use. Yeah, this is, I strongly agree on that. I think that I would need the support of a technical person to be able to, no, I wouldn't need. I found the various functions this model has are well integrated. I found the various functions as are well, yeah, right. I thought there was too much inconsistency. No, not too much, but a little bit. I imagine that most people would learn to use this model very, yeah, quickly. Cumbersome to use. What's the meaning of this? I'm sorry, I don't know this. Okay, so a little bit. Yeah, I felt confident about using. Yeah, I need to learn a lot of things before I could start. Not agreeing on that much. Yeah, let's complete the other one. Gemini. Next. How mental demanding was this task? I think above the average. How physically demanding? Uh, not that much. How hurried or rushed was the pace of this task? Um, I think it was like in between. Um, I say 6. How successful were you in accomplishing your task? I think I did pretty well. Yeah. How hard did you have to work on to accomplish what you did? Um, Not that much, but um, I would give 7. How discouraged, irritated, stressed, and annoyed were you? Actually, I did not. Yeah, this was all from my side. Thank you.